Welcome to Wildcat Science with Mrs. Haugo. This is Chemistry, Chapter 1, Section 1, and we are in Part 2. So today we are going to talk about mass and weight. We're going to start out the video with these things. They are not the same. They are often used interchangeably in everyday speak, but they are not the same in science. So mass is a measure of the amount of matter, and it is measured in grams or kilograms. And weight is the measure of the force of gravity, and it is measured in newtons. So if you remember, we talked about this freshman year. Force was measured in newtons, and weight is a measure of force. It's how much force is gravity pulling down on your mass, or the mass of an object. So let's look at the difference by calculating our masses in kilograms and our weight in newtons. So grab a calculator or something that you can calculate with. Okay, think about what your mass is in pounds. Doesn't need to be exact for this. My mass right now is 125 pounds, and then to convert that into kilograms, I'm going to divide by 2.2, and so I have a mass of about 57 kilograms. So if yours is in the range of about 45 to about 120 kilograms, then you would be in the right, you did your math right. If you got 400, you flipped it around. Okay, so you have your mass in kilograms, and then to convert to your weight in newtons, you're going to times that by acceleration due to gravity, 9.8. Well, let me do it here. So times 9.8, and my weight in newtons is 557, roughly 557 newtons. So your range should be somewhere between about 450 newtons to about 1,000 newtons. If it's nowhere near that, then you'll want to redo your math. So my weight is roughly 600 newtons, not 125 pounds. So the difference between mass in English, the English unit system, mass in the metric unit, and weight. So equal masses mean an equal amount of matter. So for example, 1 liter of water has a mass of 1 kilogram, and it has the same mass as 1 cubic meter of air. So they are not the same size, but they have the same mass, which means they have the same amount of matter in them. They have the same number, roughly the same number of particles, same amount of matter. It would be a little bit different number of particles because they have, it's water versus like oxygen, carbon dioxide, and stuff like that, but roughly. So equal size does not mean equal mass. For example, a brick and a foam block of the same size do not have the same mass, which means they do not have the same amount of matter, even though they are the same size. Okay, looking at our books, we have a brick, and it would have a mass of about 1,600 grams, and a foam block of the same size would have a mass of about 30 grams. So you know that those two things, even if they're the same size, are going to have different masses. You know that intuitively. So just taking that next step, they don't have the same amount of matter in them. So size is not a good measure of the amount of matter. Another example is 1 liter of water and 1 cubic meter of air have the same mass, but they are definitely not the same size. So looking at our liter of water, it's about this big. It has a mass of 1 kilogram. And then a cubic meter of air was quite a bit larger. So that would be, you can't even see my arms. but it would be about that much. So this whole space up to, if I were to stand up to about my hip, and then the space between the wall and me and my arms going out. If you can imagine, like 3 feet by 3 feet by 3 feet, that's a cubic meter of air. So they have the same mass, but as you know, those two things are not the same amount, not the same size at all. So what should we be using? Volume. So that is going to be what we should measure size in, and that is the amount of space that matter takes up. And in the metric SI system, we're going to be using milliliters, liters, and then cubic centimeters. So if we're looking at liquids, a milliliter is about 5 drops. A liter we've looked at before, and a cubic centimeter would be a block that's like that big. And as I mentioned, volume is not a measure of mass, and it is not a good measure of the amount of matter in something. So something I want you to memorize, it will make your life easier, is 1 milliliter of water has a mass of 1 gram. So that's a good conversion when we're dealing with water, and this works with water only, that 1 milliliter will have a mass of 1 gram, and 1 milliliter of water takes up 1 cubic centimeter. So that works out nicely, and when we're dealing with water, that conversion will happen quite a bit, and that happens because of density, and water has a density of 1. So what is density? Density is a quantity that relates mass of a substance to its volume. And it can be described with a mathematical equation. So we don't have to talk about like, oh, this is dense or not dense. We can actually get more specific, which is really helpful in chemistry. We can get a number. It is 0.81 grams per cubic centimeter or 5.2 grams per cubic centimeter. So D equals M over V, and the unit we will often use is grams per cubic centimeter. And this is a characteristic property. It doesn't matter how much you have, it will always be the same for that one substance. If you remember from freshman year, we talked about characteristic properties like density, boiling point, melting point, stuff like that. So the density of water is 1, and pure water is always 1, no matter if you have a little bit of water or if you have a swimming pool full of pure water. It will always have a density of 1. And that is another thing that I need you to memorize. It will make your life easier. Water's density is 1 gram per cubic centimeter. So let's take a look at page 11 in our book. Here on page 11 on table 1.2, they show you some densities of common substances, starting from a very dense substance, platinum, which is 21.5 grams for every cubic centimeter, and becoming less dense, lead, iron, titanium, aluminum, glass, granite, concrete, nylon plastic, rubber. Water is being 1, and now these things will not sink in water, but these things down here will actually float. They are less dense than water. Polyethylene plastic, ice, wood, oak or pine, and cork. So, what about density? Let's talk about a couple more things. So one way of calculating density is you're going to need to know the mass and the volume. So if it's an irregularly shaped object, the mass is easy enough to get on a balance, but then you would have to do water displacement to figure out the volume. And this is something we did freshman year, if you recall. And you should be able to do calculations with density. It is just a matter of figuring out what you need to know, plugging in your numbers to the equation, and calculating. So this would be a good example to read through and make sure you are comfortable with that. So we will be doing some density calculations later, but I want to talk about pressure, which is the force per unit area, and it is measured in pascals. In the English units, PSIs, and then we will also be working with ATMs or atmospheres. The air pressure at sea level, the atmospheric pressure at sea level. So air is matter, so it has mass and will exert pressure. So let's look at page 12 and 13. Looking on page 12, you can see when you pump air into your tires, you are increasing the pressure, which means you're actually putting more air molecules in there than is in the atmosphere. And you can see that there are more air molecules, and so they're going to be pushing against the tire more, so you'll have a higher pressure than on the outside. And the pressure will be exerted equally in all directions. If you were to poke a hose with a water hose, doesn't matter if you poked it on the bottom or the top, water would still shoot out of that hole. And you can feel evidence of air pressure is going down the highway. If you stick your hand out going 50 or 60, you can feel the air. Also, if you have, another thing you could do to test air pressure is if you have an empty water bottle and you put the cap on and you try squeezing it, you know it's harder to squeeze than if you have the cap off and the air molecules can just flow right out. So you know that there is matter in there. So air is not nothing. Air has molecules and is matter. If you take that same water bottle and then you suck out the air, the air pressure on the outside will push into the bottle and crush it. So again, atmosphere has air, and it is quite a bit, it's a lot more pressure and weight than you would think. 1 square meter has the force of 101,325 newtons. That is 22,000 pounds. So that is a lot of weight and a lot of pressure, but we don't notice it because it's all around us and our bodies are used to it. One last concept I want to talk about in this video is the difference between accuracy and precision. And we do want to be precise when we are talking about precision, even though we can use those words interchangeably in everyday life quite a bit. It happens, they have different definitions, but it happens quite a bit. Okay, so being accurate refers to how close a measurement is to the correct measurement. So if the mass of something is 10 grams, if you have a measurement of 10.1, that is accurate. And then precise refers to how close a set of measurements are to each other. So if I have somebody mass something, a whole group, the whole class mass something, and one person got 14.1, another person got 14.2, another person got 14.3, then that would be precise. You guys are all pretty close to each other. So a good way to visualize this is thinking about like a dartboard. So if you are accurate, you're going to be hitting close to the middle. So if you are accurate and precise, perhaps you'd have 3 arrows and they're all in that center bullseye. Oh, by the way, I would like you to make these drawings, and you could probably make them even a little better than me. So you would be accurate. Precise means that you are close to each other. You can see that these arrows are not accurate. They're not close to the ideal or correct measurement, the center of the bullseye, but they are very close to each other. And so precise means how close a set of measurements is to each other. In our next video, we're going to be learning about significant figures. So I want everybody to start getting amped up about that now. I will see you later. Bye.